So all of space is filled with this stuff called plasma, which is like ionized gas, so it's separated. The particles are separated into ions and electrons. And plasma behaves really weirdly because of that separation, so it reacts to electric and magnetic fields in a way that like stuff here on Earth doesn't. So in space, like the biggest forces you need to worry about are like magnetic and electric fields, and this process called magnetic reconnection where things go flying. So anyway, it might be most simply described as heliophysics as the study of plasma, but that doesn't make sense to most people, so we get into these long things. So yeah, so the sun is made of plasma, and then it releases the solar wind, which is also plasma, and then out of the edge of the heliosphere that I mentioned, where it interacts with interstellar space, that's like the boundary between two different kinds of plasma. So a lot of plasma. Let's see. Is Jim on his way? All right. Let me think. I guess I can talk about some of our missions. Obviously, Parker Solar Probe, which you'll hear a lot about. We have some cool speakers who are about to talk with you. Felipe's there in the back. Betsy just stepped out, but her demo, she's going to do a demo for you. That's going to be really cool. But some other missions, we obviously have quite a few missions that study the sun, although Parker Solar Probe is our first one to actually go there. But we have a bunch that sort of orbit around Earth or near Earth and look at the sun with cameras. Voyager is actually part of the heliophysics portfolio now because of it's flying through that edge of the heliosphere that I talked about. So it's making measurements of that plasma. And like, personally, I find it shocking that the instruments are still working 40-some years later. But it's awesome, and we're learning a lot about the interaction between sort of the very edges of our sun's influence and interstellar space. But we also have missions that study the effects on Earth. So this is Jim. He will tell you about all of this in more detail. But just to quickly wrap up, we also study how the sun's activity influences Earth. So we have missions that look at the magnetosphere, Earth's magnetic field, and how that's influenced by solar activity. We've had missions that have looked at the processes that create auroras. We also are looking at the processes that create these clouds called noctilucent clouds. I'm not going to explain the physics of that because I don't know. But basically they are night shining clouds, so they're made out of ice crystals. Jim's nodding. And they reflect sunlight in a way that other clouds don't. And so I've never seen them in person, but the photos, they look really, really cool. But we have a satellite that actually looks at them from above and sort of tracks how they form as a barometer for understanding other processes in the upper atmosphere. And that's where I'm going to end because Jim is here.
All right.
Sure. And actually, really quick, Kevin. I'm coming to talk to you, yes. Okay. All right. It's on you.
Oh, okay. I'm Jim Spann. I'm the acting chief scientist in the heliophysics division up at NASA headquarters. And super excited to be here to witness this launch. What I want to do is just give you a brief overview of what heliophysics really means and why we study it and why it's important and how Parker fits into the picture. So heliophysics really is the study of our sun, our star, and its connection to our planet, our home planet, as well as in understanding that connection, it's really all the physics. There's a lot of plasma physics, space physics, a lot of phenomena in those arenas that folks in our discipline are trained and learn to deal with. And then how do we study that in the best possible way is to develop instrumentation to go observe and measure the phenomena so that we can compare it to our theories and models. And so understanding the connection between the sun and the earth, and then how that applies to other planetary systems within our solar system, and eventually, as we are now discovering more and more exoplanets, perhaps things that we study here in our own local community, in our own solar system, how that might apply to habitability, search for life elsewhere. And so heliophysics in some way actually it's very interesting because it's a little bit of the glue that kind of connects connects all of the other NASA science disciplines. For example, we have Earth science. So heliophysics kind of studies the interface between space and our Earth's atmosphere and what that interface is. We have planetary science in NASA Science Mission Directorate. And so heliophysics, again, as we try to understand all of the interplanetary space between the planets and the sun, that's the realm of heliophysics. And then heliophysics is all about studying a star. It's our own star. So what we learn about our own star applies to astrophysics, which is yet another discipline within Science Mission Directorate. So heliophysics, in some sense, touches everybody and is kind of the glue that connects everything. So that's one way to think of heliophysics. So as we are studying this connection between the sun and the Earth, there's actually a very strong applied component. It's as a scientist, there's nothing more that kind of excites me than trying to discover, observe something new and totally that we can't figure out, and we try to understand it. So you want to think of it as curiosity-driven science, which in and of itself has strong value. But there's a very strong applied component to heliophysics as well, especially as our society becomes technologically dependent with communications. I mean, y'all are all into that. All of us are. I mean, everybody carries a little computer in their pocket, right? So, and so the point is that as we try to understand the environment and of space, think of it as space weather. How many of y'all have heard the term space weather? Oh, shoot, okay, you're all good. All right, so the fact is that understanding the variability in space, how it affects satellites, how it affects communication, how it affects ground systems on the ground, is all the realm of heliophysics, and that's part of the applied component of heliophysics that has actually, over the last several years, gained a little bit more attention as we pointed to the fact that all it takes is one giant explosion on the sun, a large coronal mass ejection, and if it's headed in the right direction and the magnetic field's oriented in a certain way, we could have this huge magnetic storm here on the Earth that would really impact a lot of systems. And are we ready for it? Well, we're getting there. We're trying to understand the impact. We're trying to be able to predict that. Heliophysics is right smack dab in the middle of all of that activity. So heliophysics has a very strong component of understanding, providing new knowledge of how a star operates, our own star functions. Parker particularly is focused on addressing some questions that have been around for 60 years and we still don't understand. How come its atmosphere is so much hotter than the surface? What causes the acceleration of the plasma, of those particles that cause the space weather here in our own planet? So, very focused on some fundamental science questions that we don't understand. Being able to address those in a very tangible way by actually going there with Parker will open up, will answer a lot of questions or provide guidance to astrophysicists as they study stellar systems elsewhere. Will give us a lot of understanding about the possibility of habitable worlds in other stellar systems as well. And finally, it'll help us better understand about how the system between the sun and the Earth, and understand the Earth as a system, it'll help us better be able to deal with that as well. So, heliophysics in the sense, glue that connects everything. It's important to you if you use a cell phone or watch TV or any of that sort of stuff. So, everybody's impacted. It's a great field to study. I'm not sure what else to say, but is this a Q&A also, or? Okay, there we go. So.
I have to ask you this question.
Sure.
Because you seem like the right guy for it. I'm very interested in the interplay between the solar dynamo, the interior of the sun, and which I'm sure we're going to learn a lot more about with this probe. But the interplay between how that affects, solar weather and CMEs and the things that we really need to predict, versus what they call the planetary theory of solar variation and how the rest of the solar system is affecting that. But my question is, in your opinion, what's the key predictor for solar disturbances, CMEs? Is it more in the solar dynamo, or is it in the...
Oh, wow. Okay. So the answer is a yes to all that. Because it is really a very connected system. So it's difficult to say, okay, this is the key thing that once we understand that, everything's going to fall into place. Because quite frankly, we're not that smart yet, okay? So the point is that it is an incredibly complex system. Understanding the interior of the sun is incredibly important to understanding what happens out at the surface of the sun, which in turn helps us understand what active regions are going to become active and explode. And so you can see that there's this whole chain of connectivity that takes place that we just don't completely understand yet. We have missions that have launched. SDO, for example, was in stereo, our solar missions observing the sun remotely to really try to get a better handle on the interior of the sun. Helioseismology is a field that is kind of developed over the last 10 years or so, in which we, using observations, we try to understand what's going on in the interior of the sun. There are just too many questions that we don't have answers for yet. Our observations such as Parker, in conjunction with the remote sensing, are going to certainly give us a much better sense of what's going on. But I just got to tell you that it is a very complicated system. So there's not one thing that it's really, we're trying to, it's a little bit like herding sheep. You got one sheep going out there, so you go out there and you address that question. Before you know it, 3 of them are going over here, or it's that sort of thing. And so we are really trying to get our arms around it. That's to me, that's one of the reasons I love my job, is that as we see another sheep going off, and say, well, what sort of mission or what sort of investigation do we need to do to go corral it and bring that knowledge back into an understanding. And so it's quite a creative process to try to figure out, well, how can we address that question? And there are just so many of them, I can't point to a single one. I will tell you, though, that there is a lot of focus on looking at the magnetic field structure near the surface of the sun, which is believed through magnetic reconnection to be the mechanism by which these explosions do occur, and a lot of energy and mass and momentum is released. And so, right now, I'd say looking at the magnetic field structure on the surface of the sun and how that interplays with reconnection is a pretty hot topic, no pun intended.
What's your predictive accuracy? Well, percentage-wise, I mean, or can you express it?
Predictive of what?
Of being able to predict when, large CMEs would explode.
I don't have a number. I think we can see some regions on the sun that look rather active, but we're not in a place right now where I can say, that's got a 10% of doing whatever.
Yeah, there's a lot of work to be done.
And remember that even though something is very active on the sun and a CME comes off, that doesn't mean it's going to be geo-effective. What I mean by that doesn't mean that it's going to impact the Earth.
Right.
There's still the whole process of going from the sun to the Earth, and whether it's actually going to strike us, and when it does strike us, how is it going to couple in with our own magnetic field? And so, there's just a lot of parts. Yes, sir.
Curious about last year's eclipse. How out of the citizen science that was done during the time, I know there was a lot of reproduction, the editing experiment, that sort of thing, and the pure science that was done as well. How much have you learned as a heliophysicist from last year's eclipse, and did any of that affect planning with the Parker mission?
So the eclipse, directly planning the Parker mission, probably not, just because of the phasing. I mean, by the time last year was around, Parker was it was unless something fantabulous we discovered, we weren't going to change what Parker was doing. So from that perspective, no. However, I will share with you that the eclipse did provide us, because we had such a huge capability with a citizen science to observe this eclipse in an organized fashion greater than I think any other eclipse had been studied. We are learning a lot about the impact, bless you, a lot about those peculiar events and how that affects our atmosphere, upper atmosphere, and so the data for that is, the analysis for that is ongoing, but we're in the process of trying to collect all of that so that we can, as we prepare, as y'all know, these eclipses occur about every 18 months or whatever. The next big one in the continental U.S. is, what, about 6 years away now. It was 7 last year. As we prepare for another, perhaps a big old giant event in terms of where we collect a lot of information from citizen science, we want to know what it is that we learned from this event so that we can form a baseline to now add to that. And so that information is being collected, and we're getting ready to, well, collect it in one place and then publish it is the plan. Yes, sir.
Correct me if I'm wrong with any of this, but I seem to recall that the sun rotates as well, like the Earth does, but it rotates faster on its equator than at its poles.
Yes.
Okay, how does that affect heliophysics?
Okay, so, so that's really just, really at part of the core of what heliophysics is, because we're trying to understand the dynamics of the sun. So you're right, the sun is a ball of gas, right? And so there's what's called differential rotation. So the equator region, the surface of that gaseous ball tends to rotate at a different rate than the polar regions. And so what that does is that causes some sort of shear and disturbances in the surface of the sun. And that then plays into the dynamics of the sun. There are, if you look at sunspot plots, there's something called the butterfly plot, which kind of shows, if you just map sunspots as a function of time on the surface of the sun and kind of lay it all out, project it on a map, kind of like we do on our globe, we project it on a flat map. You'll see that these sunspots tend to form these shapes that look like butterflies, so they call it the butterfly plot. The point is that all of these things are indicators of how the sun works, how that dynamo plays into it, and trying to correlate the more easily observable things such as sunspots with the complex theory of the dynamo and the inner dynamics, and how these active regions kind of percolate or bubble up from the bottom. Understanding that differential rotation is important to do that. So it's just all part of that very, very complex chain of events that we're trying to unravel. Yes, ma'am.
Is there a main theory for why the corona is so much hotter than the surface?
Well, I think there are a couple of theories on there. Now, that's not my particular area of expertise. I think they're by going in and actually going into the outer parts of the corona and observing literally what's there will help us differentiate between the various theories. There are some proposals that folks are suggesting that we fund in order to do some modeling and then to compare with those observations that we make. And so, yes, there are a couple of theories, and again, when we get some of the PIs and you can kind of pin them down a little bit more on that. But that is part of the reason why we do this. Not only is it an opportunity of discovery, because undoubtedly, you know, we'll have great plans, and we do have great plans about what we're going to observe. We don't know what we're going to find out. So that discovery nature, so we're going to find out some things that we don't expect, but we are going to be able to find out some things which will help us point to one theory or another. So, yes, in the gray, and then in the...
Question, you working on light cell too, and what sort of information are you expecting to get back from that light cell? Light cell? Yeah. Not familiar with that one?
No, I'm not sure what you mean by light.
It's a CubeSat that they're going to launch.
Oh.
And it's like with this cell that's going to unfold.
Oh, okay, okay, solar cell stuff. Okay, yes. So what was your question then again?
I was wondering if you were working on it, what kind of information you were expecting to get back from it?
So I'm not working on that. I do know that as we are developing the technology to deploy solar cells to help us essentially tack like you're sailing on a on a lake out there, to move in a little bit closer to the sun and perhaps even kind of station keep, kind of sit there and kind of hang out. I do know that that's one of the strong motivations for the solar cell technology, and as the opportunities for people to propose and launch those where it's pretty tough, this folding kind of something really tiny and then unfurling it and have it work in space and control it is, well, we're still learning how to do that. So personally, I'm not working on it. Yes, there are several groups working on that. In fact, I just came from a small satellite conference in Utah just yesterday, in which several proposals of CubeSats for deploying solar cells were presented, and so it's an area that a lot of people are looking at. So I'm anxious to see, as we get more opportunities to deploy those, to see kind of how they are, how we're able to make progress in that area. Eventually, we want to instrument those solar cells so that we can put instruments much closer to the sun, get a earlier preview of the solar wind, essentially. Yes?
I have a question about the heliosphere. So everything that I've kind of seen about it, it appears to just be this bubble. And everything I know about the sun, it appears to be this constantly shifting, never in one way kind of structure. Does the heliosphere kind of wiggle and adjust, or is it kind of a constant sphere?
It's so it does wiggle and adjust. Now there's wiggling and there's wiggling. We don't know. That's an area of heliophysics, because again, that's part of our whole solar system and how our solar system interacts with interstellar space. That's kind of the boundary there. It kind of forms the heliosphere. It does have a shape, and it does, as the sun burps and does whatever, eventually those disturbances end up in affecting the boundary and how our solar system interacts with the interstellar space. As y'all know, Voyager, we've got 2 spacecraft that have been around like forever, longer than many of you have been alive, and they, at least one of them we believe is already out in interstellar space. The other one's kind of making it through. We're still trying to understand that boundary because it does wiggle and move back and forth. We've just selected a new mission called IMAP, which we're just beginning now, but we hope to launch in, or at least scheduled to be launched in late 2024, which will actually image that boundary. We have a precursor mission called IBEX that has done, kind of given us an idea to discover this kind of peculiar ribbon that they call. Anyway, so that is an active area of research of heliophysics, and yes, it is determined largely by what goes on with the sun, but it takes a long time for whatever happens at the sun to actually find its way to the boundary there, like years, and so understanding what that connection is part of what IMAP is going to be doing. So, good question. Thank you.
We have time for one more question.
Yes.
So, this is from one of my followers. The 1859 mass ejection, how does, are we prepared for another thing like that? And is that kind of thing the thing that you're specifically looking at?
So that's the so-called Carrington event. It was a ginormous coronal mass ejection, and of course, you got to think of 1859.
Yeah.
What was our technology then? Well, we had wires and telegraph wires and stuff. And yes, it impacted that sort of thing. Is that the type of thing we're worried about and preparing for? Yes, and I'm going to answer it. And so now we're talking about space weather, because what happens on the sun, how it impacts us here on the Earth. So that's the stuff of space weather. And I like to think of space weather kind of in 2 different ways, and much in the same way that we think about terrestrial weather. The Carrington event was like Katrina to New Orleans, right?
Mm-hmm.
It came, of course, you know, back then they weren't expecting it. Of course, you know, we had some sense that, you know, something was going to happen to Katrina. That's what we're trying to do, is trying to prepare ourselves. If something does happen on the sun, we don't have a whole lot of time to get ready for it. But as we are able to predict things before it happens on the sun, now we're talking about being able to be prepared for a large event like that. So that's kind of at one extreme of space weather. That's the incredibly impactful but somewhat rare event. You know, the last one occurred in 1859, right? So it's been a while. Then there's the other extreme of space weather, and that's like when y'all came here today, you probably checked to see, well, do I need an umbrella or not? You know, it's the daily variability. So space weather also has that aspect of it, and that's something that folks who are who depend on communications, not only in the civil arena, but also in the Department of Defense, is a huge deal for them. So that's a little bit more the day-to-day variability. It's the weather that occurs every day in space. So understanding those, that phenomena, how the ionosphere varies on a day-to-day or an hour-to-hour basis. We know, you know, shortly after sunset, around 9 o'clock local time in the evening, or 2 or 3 hours after sunset, you know, the ionosphere kind of gets disturbed a little bit. So why does that happen? What causes that? Yes, the sun does play a role in it, but the sun doesn't necessarily drive it, because whether the sun's doing something or not, this stuff still happens, and it still does impact us. So yes, we are preparing for the Carrington event, and are we totally prepared yet? Well, we don't know, because it's been since 1860. And life is a little different nowadays, and the impacts. So that's all. Many agencies are working together to address that, but also many agencies are working together to understand the day-to-day variability, so that farmers and people who use GPS and our boots on the ground and with military folks and airlines can help us live our day-to-day lives.
Great, thank you so much, Jen.
Thank you.
Appreciate it.